My name is Robert O'Brien. I work here at the NFSTC. I've been here for 2 years. Before that, I worked for approximately 5 years at the Florida Department of Law Enforcement in Pensacola, Florida as a DNA analyst. And my presentation is basically when I looked at the MinElute, the first thing I did, the first part of this presentation, as you'll see, is I kind of went, so like kind of a go for broke attitude with it. You'll see that you all have a user-developed protocol. It's kind of like one of the first protocols that came out. It wasn't developed by me. And it was to do like 4 washes, and that's what I did. And so these are my results. And then the second part of my presentation is going to deal with, I started to manipulate the number of washes I did, and I also did some work with the robot. And I compared the results. Okay, so the first part of the study was conducted before the NDIS ruling and what was constituted a low copy number sample. So as a result, some of the samples I did use did have stochastic effects, dropout, high stutter, all the things that are associated with low-level samples. And I did that on purpose because I wanted to see what effect MinElute would have on low copy number samples, on samples that showed problems during amplification. Does MinElute fix it? Does MinElute make it worse? Or does it, if you see it before, you're going to see it after? I wanted to know. And then after the ruling was released, the second part of the study, I kind of used approximately 100 picograms, so 0.1 nanogram per microliter concentration is what I used for the second part of the study. Even though that is lower than what they were saying, the value that's being quoted is, I believe, about 200 picograms. Even though it is lower than that, I didn't really have any stochastic effects in that data. I did have some peak imbalances, but I didn't have any like dropout or anything occurring in the samples I used. Okay, so the MinElute manual procedure, the reagents that come with the kit, as Matt talked about earlier, we have the buffer PB, the binding buffer, the buffer PE, which is for the washing, and the buffer EB, which is your elution buffer. You need to have ethanol, about 96 to 100% ethanol in the lab. You get the MinElute spin columns. You get sterile microcentrifuge collection tubes. You also, for the robot, you get the 1.5 mil microcentrifuge tubes, but manually you just have to provide your own. You'd have, of course, have to have a microcentrifuge, and then the pipettes you use are usually the 10, the 200, and the 1,000 microliter pipettes. And then all work, of course, must be performed in your post-PCR room because you are handling amplified DNA. Okay, so to the amplified product, what you'll do is add a volume of a buffer PB that is equal to 5 times the volume of the amplified product. And usually you add it, you just mix it up and down a couple of times, because when you first add it, you'll see there's a difference in consistency. And as you mix it up and down, you'll get a more homogeneous mixture. And depending on the volume of the amplified product, for example, a 50 microliter reaction, if that's what you're doing at your lab, then you won't be able to mix it in the amp tube. But for a 25 microliter reaction, I was actually able to mix it into the actual amp tube itself that came off a thermocycler. And then once you mix it in there, you're going to remove the entire volume of buffer PB and amplified DNA and place it into the spin column. And you spin for 1 minute at 13,000 RPM. And this is the DNA binding step. Okay, so that, it's not too clear, I know, with the lighting. It may not be easy to see, but y'all will see them today and use them today. But that is actually the column assembly. You've got the top part, which is the purple column, which has the membrane in it that you saw earlier. And then it comes with that bottom sort of like collection tube. So after spinning, you're going to discard the flow through and then reassemble the spin column in the collection tube. And before the next step, you have to prepare the buffer PE. I mean, this could have been prepared in advance. This is where you add ethanol to the buffer PE. The bottles you get will actually tell you, will have the buffer PE in it already, concentrated, and it will tell you how much ethanol you have to add to bring it up to the full volume you need. And then you'll add 750 microliters of buffer PE to the spin column and spin for 1 minute at 13,000 RPM, and you'll discard the flow through. So this is the wash step. Now, the protocols that QIAGEN has now, which we'll get a copy of that in the lab, the bench protocol, has one wash step. When I did my study, I started with 4 washes. I did 3, 2, 1, and I actually did a sample with no washes because somebody questioned that at the American Academy. What would happen if you just added all your amplified product? Wouldn't you get the same increase? But obviously, I think most people here know you won't. So after flow-through is discarded, you reassemble the spin column and you spin again for 1 minute. And this is when I think Matt talked about getting all the excess ethanol off the silica membrane earlier in his presentation. And then you're going to transfer now the spin column to a new sterile 1.5 mil microcentrifuge tube. You place 10 microliters of buffer EB directly onto the membrane, and then you're going to spin, and you have to be careful not to touch. Obviously, you don't want to poke through your membrane with your pipette tip. You'll allow the buffer EB to sit there for approximately 1 minute, then centrifuge for 1 minute again at 13,000 RPM. And at this point, this is the step where you're eluting the DNA, your concentrated DNA, off of the membrane into the collection of the 1.5 mil centrifuge tube. And the final elution volume is usually between 8 and 10 microliters. And before the sample is placed on the genetic analyze, must be heated and snap cooled while in formaldehyde. We did a little test with some trainees at Baton Rouge, Louisiana State Police Lab, and they don't have the heating and snap cooling as part of their procedure. And I automatically always did it, so I did not actually know that it was something that was necessary to do for the MinElute procedure. But what we got is we got a lot of shadow bands occurring when we did not do the snap and heat cool. So I spoke to Kathy Press, and she said, oh no, you have to do the heat and snap cool for this to work. And that's when we realized what the problem was, why it wasn't working that well at that lab. Okay, so the first part of the study, like I said, I tested it on all the commercially available amplification kits to determine first if it would work on all kits and if its effects would be similar. The number of washes done for this study was 4, which was the number of washes recommended in a user-developed protocol. Like I said, you all should all have that. And all the amplified product was put through the cleanup, and all of the resulting product was put onto a 3130 genetic analyzer. So like I said, I was kind of going for broke. I put all of the amplified DNA in there, and then everything I got left, the full 10 microliters, I put 10 microliters onto the genetic analyzer. Because I wanted to see, well, obviously, if you max out the system, the benefits, but also would it have any ill effects of putting all of it on there. Okay, so then after that part of the study, then using one kit and one concentration, certain aspects of the procedure were changed. I varied the number of washes I did. The volume of amplified product put through the cleanup process was also varied. The volume of cleanup product placed on the actual genetic analyzer was varied. And the type of sample was also altered. I did on a mixture. The purpose on the mixture was, now I've seen the results where if you have a total low-level mixture, it raises it. But this was if you have a really high minor and a really high major and a really low minor, if you can use MinElute and properly bring up the minor and be able to interpret it. So let's look at some of the results I got. So first of all, the fold increase. After post-PCR cleanup, there was a signal increase from an original peak height of 50 RFUs to a minimum of 300 RFUs in every kit tested. Now that's the minimum. I mean, you'll see in the next, my next slide, you'll see actually how high my increases did go up. But basically, everything that I tested, I had like a guaranteed increase from 50 to 300 RFUs, regardless of the kit I used. The fold increase did vary from kit to kit and also change with different starting concentrations. However, there was always an increase with the minimum being 6-fold. So this basically was actually, this is the average fold increase. So even though the average may have been 10-fold, it may have been like a marker in there that only increased 6-fold, but nothing increased less than 6-fold. But as you can see for co-filer, how high it went, it was like over a 30-fold increase, and this was doing the 4 washes. And then those are the concentrations that I used on top. Okay, so as seen in the graph, the smallest average fold increase occurred in the identifier kit, and this was a 10-fold increase. Co-filer had the largest fold increase at a concentration of 0.031 nanograms per microliter. Kits that were more sensitive were tested at a lower concentration, and at that concentration, Y-filer showed the greatest average fold increase of over 20 times. The concentrations were chosen because all of the peaks were below 75 RFUs in previous testing at these concentrations. So basically what I did, the reason why I chose those specific ones is I was starting off at peak heights that were below 75 RFUs. I was looking for concentrations where all my peak heights were below 75 RFUs. Okay, focus was then placed on the 2 large multiplexes that are commonly used in DNA forensic laboratories. So I looked at identifier and PowerPlex 16. And the graphs for these are 0.0625 nanograms. So this is identifier, and it's kind of hard to see the before cleanup, the yellow, But basically, the before cleanup, that was the peak heights of when I just ran. That was what I just ran the sample at. So as you can see, they're probably maybe around 100 or something RFUs. And then after 4 washes with the MinElute system, those are the RFU peak heights they increased to. You could see the lowest one is probably maybe around the 800 RFU mark. And of course, you saw the D5 went all the way up, which would probably be off scale for some laboratories. But once again, this is with 4 washes. I'll show you later on when I vary the number of washes that they don't all go that high as you vary the number of washes. Now, multiplex 16 had a larger starting baseline. But as you can see, the increases, it also, of course, went up quite high, a lot of over 7,000 RFUs. I think, the lowest one there is at 2,000 RFUs. So basically, that was just the increase, I got. So even though on average the fold increases are high, there is some variation within the multiplexes from one locus to the next. All samples were analyzed in triplicate, and the results were averaged together to yield these results. Okay, once it was established that there was a fold increase, then the next thing I wanted to look at was basically the quality of the data. So I looked at -A, I looked at diblobs, high stutter, dropout, drop-in, and heterozygosity. So first of all, -A, we've all seen -A. If -A was not present before, it was not present after the cleanup. However, if it was present before, I did see it. Actually, it increased a little bit after, and it was actually more clearly defined. So this is the -A before the cleanup. You could see the little shoulder peak there, and it's approximately 38%. You'll notice, let me go back. And it's not being called by GeneMapper at this point. So therefore, you had -A present. It was not distinguished from the main peak by the GeneMapper program. Now this is it after. So after cleanup, the -A is now at about 50%. It's a lot sharper, and now GeneMapper actually did call it. So GeneMapper did recognize it now. So the -A is now at a higher level and is more distinguished from the main peak. The -A is now recognized by GeneMapper ID and is labeled. Okay, so the results of this were not that surprising to me because MinElute is supposed to clean up your sample, increase your peak heights, and produce better quality data. And that's basically what it did. Yes, it increased the -A a little bit, but the -A was there to begin with. -A is a byproduct of the amplification process, as we all know. So therefore, MinElute will not fix that. If you want to fix -A, for those labs that do have protocols, you fix it by doing an additional extension. So it's fixed in the amplification process. It's not going to get fixed by MinElute. Okay, diblobs. So diblobs are artifacts that are common to most kits and are often documented by the manufacturer. The example of the diblob shown in the next 2 slides was from multiplex 16 at the D5S818 locus. Okay, so this was the diblob before cleanup. I also want you to make note of the peak height of the 11 there. It's at 305 RFUs, and the diblobs at 37 RFUs. Now this is after cleanup. Okay, yes, my diblob did go up a little bit. It's now 84 RFUs, but my peak height went up over 10 times. So obviously the peak height increase is not proportional. So even though the diblob did increase in size, it did not increase in proportion to the main peaks. In other instances, the diblobs decreased in size, and some were even completely removed after cleanup. So like I said, I'm giving you all here like the worst case scenario, which to me was still a good thing. Since diblobs are from excess dyes in the kits, it would be reasonable to assume that the MinElute kit would help reduce or remove them in some way. And because the kit is designed to remove excess primers and dyes, that's why I expected it to have an effect on reducing the diblobs. High stutter. Sometimes we see high stutter in data. High stutter could be a sign that you may have a mixture, but then sometimes high stutter is just simply you have high stutter at a specific locus because you have no other signs of a mixture. So this is it before cleanup. The stutter is at 36 RFUs. Before cleanup at the D16S539 locus, the stutter cutoff percent was above the stutter cutoff percentage and was assigned an allele called. The stutter percent was 14.4%. And this is it after cleanup, it's still present. So after cleanup, the high stutter was still present and was still assigned an allele called by GeneMapper ID. The stutter percentage following cleanup was 13.6%, which is a little lower than the original 14.4%. However, the decrease was not really that significant for me to basically make a statement that MinElute will reduce stutter, because I did not really see any signs of that. But one thing it will not do is increase your stutter. So if your stutter was high to begin with, it's not going to get higher after you do MinElute. So dropout. Once again, we all seen dropout. When you're dealing with low-level samples, dropout is a very common thing to happen. Alleles which are present in the sample are not amplified during the PCR process and therefore not seen in final data. So this is an example of DYS19. Before cleanup, that marker was completely dropped out. And you'll see the 15 at the DYS437 is at 120 RFUs. Now the DYS437 is at 1700 RFUs, but the DYS19 is still not there. So if it's not there before, it's not going to be there after. So MinElute's not going to fix that. Once again, it's whatever you have there before, you're going to see after. You're just going to get levels raised with respect to your peak heights. So after cleanup, there's still dropout of the allele at DYS19 locus, even though the peak at DYS437 did increase in peak height. Dropout is a byproduct of low-level amplification, so any attempts to fix it would have to be conducted at the amplification setup, not after the process is completed. Therefore, it is not surprising that MinElute would not affect dropout. MinElute does not cause or prevent dropout. If dropout was present prior to cleanup, it will be there after cleanup. Drop in. This is basically when you see, sometimes you see random peaks not associated with the data are seen. With MinElute, this phenomenon appeared to have occurred, but on close examination, it turned out that it didn't. This is actually the after MinElute slide I have here first. You see the 15 and the 17, one's at 115 RFUs, one's at 94 RFUs. So they're present in this slide, and like I said, this was after. So at first, those peaks appeared to be drop-in because I did not see those peaks before. Because this is the before sample. And as you can see, if you look at the left-hand side there, you will see that the RFU scale, I mean, you're talking about something that's maybe 6 or 7 RFUs, so it's obviously going to be buried into your baseline. And that's where the 15 and 17 would have been. So seen in the previous slide, the 15 and 17 peaks are clearly not discernible from the baseline, thus reinforcing that drop-in has occurred. However, the correct profile of the D3S1358 locus for this sample is a 1517. So even though it looks like it's part of the baseline and it looks like it was some random drop-in, it wasn't, because it was actually the correct profile is what was pulled up by the MinElute afterwards. So every time I saw what appeared to be drop-in, it actually corresponded to the correct profile. So since the RFU increase ranges anywhere from 10 to 30-fold, it is reasonable to believe that DNA present in the original sample was just so low that it could not be discerned from the baseline. I mean, if you have something that's at 6 or 7 or 10 RFUs, and you have a 10-fold or 20-fold increase, I mean, you're going to be 100, 200 RFUs. So it's something that at one point you can't discern from your baseline. From the other point, it's going to be this peak that's just staring at you. The results demonstrate that MinElute is a very good tool for detecting low-level samples or contamination that was not previously visible. So in short, MinElute will bring all things to light, even those things that you don't want to see. So yes, if you do have low-level contamination, you will definitely see it. If you don't see it before, you'll definitely see it after you do the MinElute process. Okay, the heterozygote peak height ratios. Differences in peak height ratios were not only seen before and after cleanup, but were also seen within the triplicate set of samples as shown on the next slide. So this is just all pre-cleanup, and this is the same sample done in triplicate, and that's just how the peak height ratios differed within the triplicate. And then this is it after cleanup. The peak height ratios differed again. So these are differences were seen between pre and post cleanup, and also within the triplicates themselves. So I don't really attest anything of this to be actually caused by the actual MinElute process, since within the triplicate there were variations of the actual peak height ratios. So MinElute successfully yielded an RFU increase in all samples tested. This increase brings data to a level that crosses most, if not all, laboratory thresholds. Any stochastic effects caused by low-level amplification were carried through through in the MinElute kit. The stochastic effects were more clearly seen because the peak heights were higher after cleanup and no longer hidden in the baseline. So basically, things that may not have been so clear before will be more clearly seen after. Okay, so now once I established that the MinElute kit works on all the kits, then I went to the second part of the study. And basically only used identifier kit for this part of the study, and the concentration I used was 0.125 nanograms per microliter. Even though this is below the official recommended amount of 0.2 nanograms per microliter, no stochastic effects were previously observed at this concentration. So the following parameters were studied: the number of washes, I did the robotic versus the manual, the volume of cleanup product added to the 3130 genetic analyzer, and the volume of amplified product put through the cleanup process, and also the effect of MinElute on mixtures with defined major and minor contributors. And all experiments were conducted in triplicate. So volume of sample. Okay, during the poster session, the American Academy of Forensic Sciences meeting, attendees inquired why there was no data to show the effects of adding all of the amplified product to the 3130 without putting it through the cleanup process. And so basically that's what I just did that to satisfy in case I get that question again. So this is 0.125 nanograms per microliter. This is just adding it straight on. This is without MinElute, and that's what the raw data look like. So you can clearly see there are some peaks present. And you can see you have your nice Liz standard also present. This is what happens if you add all of your amplified DNA straight onto your genetic analyzer, all 25 microliters of it, or well, 50 microliters if you do a 50 microliter reaction. Basically, I couldn't even show the analyzed data because GeneMapper couldn't analyze it when it looked like that. So basically, raw data when all the 25 microliters of amplified product was added prior to cleanup, and you see the actual Liz is now suppressed, and the peak heights, I mean, you can tell that some of the peaks aren't even in as good of a shape as they were before. I mean, when you look at those peaks there compared to those there. So by adding all the amplified product to the genetic analyzer without using MinElute, there was a negative effect on the resulting data. Before cleanup, DNA was clearly seen in the sample and raw data. However, after adding all the amplified product to the genetic analyzer, all of the data was suppressed as well as the sizing standard. This could be due to the excess primers and dyes interfering with the laser's ability to accept the dyes attached to the actual amplified pieces of DNA. So let's start with varying the number of washes. So the number of washes will vary to determine what would be the most efficient way to perform the procedure manually to save on time and reagents. The number of washes will vary from 1 to 4, and in all cases, all of the amplified product, whether cleaned up or not, was added to the genetic analyzer. The results are charted in the following slides. In all cases, there was an increase in peak heights. However, the peak heights did change with the number of washes performed. Okay, so this one, this shows the fold increase with different number of MinElute washes. And like I said, this is done manually. And you could see the blue is with just doing 1 wash manually. The red is doing 2 washes. The green is 3, and then the purple is 4. You'll see the best data actually sort of comes from doing 3 washes. But then again, if you want to look at your reagents and timing-wise, 2 washes was not that much different from 3, and it saves on time and the number of reagents that you have. 4 washes was almost a point of diminishing returns, because by the time performing 4 washes actually gave me less peak height increase than I got for 3 and 2 in most cases. And 1 wash did give peak height increase nearly to a 10-fold, so anywhere from probably about maybe 6 to 10-fold I got with 1 wash. So the average fold increase for manual washes was as followed. 1 wash was about 9.5, that was the average. 2 washes was 16.9. 3 washes was 17.9, and 4 washes was 14.3. So even though there's an increase in the fold increase with the number of washes, there comes a point at which doing more washes no longer results in an increase in peak heights. Even though 3 washes gave the highest increase in peak heights, 2 washes seems to be a more efficient method because the increase of 2 washes is just a little lower than 3, and the time and reagent uses less. Okay, so QIAGEN has developed a robot called the QIAcube to perform the MinElute PCR purification process. First of all, I did a little check for contamination because, dealing with amplified DNA, that's one of the major concerns whenever you're dealing with amplified DNA. So the first thing I did was no contamination within a run or between runs was seen when using the robot. The QIAcube frees up time for the analyst to work on other tasks while the robot is performing the cleanup. And the QIAcube also allows for more consistent pipetting and eliminates human errors that could arise while working with amplified DNA. I mean, one thing I liked about the QIAcube was it would be perfect for you have your samples running in the QIAcube, and then you're setting up your genetic analyzer with your formamide and all that. And then by the time the QIAcube is finished, because it takes about 30 minutes to do 12 samples, it takes a lot less time if you do less than 12. By the time that's done, you've got your product, and you're just throwing it straight onto the genetic analyzer. So the QIAcube robot is a fully enclosed system. You always get to work with it today. All controls are via touchscreen on the outside, and once the system starts, there's no need for human interaction. That's just a picture of the inside of it. You've got your robotic arm, and then you have a centrifuge. You have a reagent rack, sample rack, and you have your pipette tip holders. Okay, before starting the QIAcube, the spin column, collection tubes, and sample tubes must be placed in the correct positions in the instrument. The QIAcube can hold a maximum of 12 samples. Fewer samples can be processed as long as they're positioned in such a way that they will be balanced in the centrifuge. Because it is a centrifuge system, if you want to basically you have to do at least 2 samples so that they can be balanced from each other, or else the centrifuge will not be balanced. Inside the QIAcube, there is a light on the robotic arm that is used to detect the positions of the reagents and tubes in the instrument. This to me is a very cool feature because basically once you set it up, it actually goes through and does a check and makes sure everything is set up correctly for you before it'll actually start processing samples. If you overfill your reagent bottle, it'll actually tell you that you've overfilled your reagent bottle. This way the QIAcube knows that everything is in the correct place before it begins. That's the rotor adapter. The tubes are placed in the rotor adapter in the positions as shown. The final collection tube and spin column are placed on opposite ends of the rotor adapter. So remember the purple spin column that was in that little tube before for the manual process? Well, you don't use that collection tube again. This is basically the rotor adapter is going to be your collection tube. The spin column goes on the side with a single cap holder, and the cap of the collection tube goes into the larger cap holder on the other side. A setup rack is provided that holds the rotor adapters while the tubes are being placed in them. And the rack is numbered 1 to 12. So that's where you would actually place your rotor adapters into there when you have to set them up. And those positions then correspond to the positions on the centrifuge. So if you're only doing maybe 3 or 4 samples, you position them in there in the correct position. So you know when you're putting them in the centrifuge, you're putting 4 in number 4, 5 in number 5, and so forth. The rotor adapter is then placed in the centrifuge. So that's the rotor adapter there. The adapters will only fit into the centrifuge in one direction. The purple spin column is positioned closest to the center of the centrifuge as shown in the following slide. So that's how they fit right there. So you'll see you have your rotor adapter just go straight into the bucket, and you see the position. And like I said, you'll be all doing this today. Okay, so now you have your sample rack. The amplification product must be transferred to a 1.5 mil tube so it can be placed in the shaker rack. You can't take your little DNA tubes, your little amplified DNA tubes, and place them in that rack. Obviously, they're too big. And because you're having the mixing process, when you're adding the binding buffer, it needs to make sure that there is enough space in there to do a proper mixing. When processing less than 12 samples, the amplicons will be placed in the shaker rack in the same numbered positions as the rotor adapters are placed in the centrifuge. It's kind of hard to tell from this slide, but you'll see it when we do the QIAcube today. These are also all numbered. So these numbers will correspond to the numbers in the centrifuge. And we have the reagents. The reagent bottles also have designated areas where they must be placed. As Matt said, this robot can be used for a lot of different applications. That's why you see it has space there for actually 6 reagent bottles. And there's probably a lot of different configurations depending on what you're using it for. But for the actual PCR cleanup, that's where you will place the reagent bottles. And then you've got the pipette tips. They are supplied by QIAGEN, and the racks are placed in the pipette tip rack holders on the instrument. You have 1,000 microliter tips in the back and 200 in the front. The QIAcube uses less than half of each rack to complete the 12 samples. No contamination was detected when the remainder of the rack was used to perform another run. So basically, I was able to perform an entire run with these tubes in place, with these pipette tips in place, then do a blank run after it using the same pipette tips, and there was never any contamination. So there's no carryover. So you can actually use the same rack of tips before, instead of having to, because you're only going. That's probably, I think that was after a run. So you may only use like maybe a half or less, and it would be a shame to think you got to throw away a half a rack of tips every time you go to do a run because you're afraid of contamination. But I didn't see any contamination going from one run to the next, and I did a run of full samples followed by a run of full blanks, and there was no contamination in my blanks. Okay, so once all the components have been placed in the QIAcube, the door is closed and it's operated via touchscreen on the front of the instrument. So that's a shot of the touchscreen there. So first you have to select cleanup on the front panel. On the next screen, you arrow up and down to get to the MinElute PCR, and you press select. You select amplification reactions. On the next screen, select standard, and this takes you to the fill-up volume screen where you press select. Your total fill-up volume must be 100 microliters. That's what your total fill-up volume has to be. So you have to put in the amount. If you're doing a 25 microliter reaction, then you have to enter that you want a fill-up volume of 75 microliters. So it knows you're putting 75 into 25. If you have a 50 microliter reaction, then you'll have to do a fill-up volume of 50 microliters because you have to total add up to 100. The fill-up volume refers to how much buffer is added to bring up the volume to 100 microliters. To adjust the fill-up volume, go to Options and use the plus or minus key to set the fill-up volume. Then save it. So this is just an example here. If you go to Options, then you go to Fill-up Volume, you can select that, and then you'll see on the bottom there that you can either go anywhere from 0 to 95. So if you have a 100 microliter reaction, which I don't think anybody does those, but if you happen to, you wouldn't add anything to it. But if you only had 5 microliters of DNA in there, you can add 95 microliters of your binding buffer to it. And then basically you're going to click Start, and once you click Start, it's going to go through a bunch of questions. It's going to ask you, did you do this? Did you put the rotors in the right place? Did you put your reagents and all that? So this is some of the results I got from the QIAcube. So 1 manual wash, 2 manual washes, and then in green we have the QIAcube wash. Now, once again, the 2 manual washes did perform better than the 1 manual wash and the QIAcube wash, but you could see the QIAcube wash performed better than 1 manual wash. So, and you're still getting a fold increase of about approximately 10-fold with the QIAcube. So the QIAcube performs only 1 buffer wash. The chart on the previous slide shows that performing MinElute cleanup with the QIAcube gives better results than a comparable single manual wash. The chart also shows that the robotic process does not work as well as conducting the manual method with 2 washes. When performing the cleanup process on the triplicate 0.0625 nanogram microliter concentration samples, the fold increases varied for the manual washes, but the QIAcube results were very close. Basically, the QIAcube tends to give you a more consistent increase every time. You see with a manual wash with 0.125, it was a 9.56 fold increase. With 0.0625 is a 7.36 fold increase. For manual 2 washes, you had a 16.96 fold increase, and then you had a 11.52 fold increase. But for the QIAcube, you went 10.44 and 9.76. So the QIAcube gave the most consistent increase between concentrations of amplified DNA. And this could be due to the increased precision associated, obviously, with robotic pipetting as opposed to a manual pipetting. Okay, because some laboratories retain some of their amplified product, in this next stage of the study, either not all of the amplified product was put through the cleanup process or not all of it was added to the genetic analyzer. The purpose was to see what type of peak height increase would be achieved if the product was left over for possible future testing. The cleanup for this part of the study was conducted on the QIAcube, and the concentration of 0.125 nanograms per microliter was used for all experiments. Okay. So this is the results of adding different volumes of cleaned up product to the 3130. So I cleaned up all of my amplified DNA, and what I did was just vary the amount of it I placed on the 3130. So if I only added 1 microliter of my cleaned up product, I got like a 4.28 fold increase. If I added 5 microliters, I got about an 8.44-fold increase, and 10 microliters, I got about a 7.86-fold increase. So once again, you can see there is a limit at which you reach where if adding more doesn't actually do anything to enhance your results beyond that. And in this way, you're thinking you get an, off the QIAcube, you elute about 15 microliters. So if you took 5 of that and added it onto your instrument, you still have 10 microliters left over for future testing. You know, if defense attorneys want it for whatever reason. I know some labs keep it and some labs don't. Okay, so now cleaning up some of the amplified product had the most drastic effect on the average fold increase. So now instead of cleaning up all of my amplified DNA, I just cleaned up some of it. When I cleaned up 5 microliters, I got a 1.43-fold increase. And when I cleaned up 10 microliters, I got a 2.56-fold increase. When only 5 microliters of amplified product was put through the cleanup process, at some loci there was not an increase in peak height. So what I'm showing you there is the average increase. So on average, it was like a 1.43 increase, but actually at some loci, I did not even see an increase. In fact, the average peak height went down at those loci. The heterozygote peak height ratios did change from before cleanup to after cleanup. After cleanup, the ratios were more consistent with the triplicate than before, within the triplicate than before. So this was something that I noticed, even though at all the peak heights I didn't get the best increase, my heterozygosity improved when I only did with only a little bit of the DNA as opposed to a lot. Like the ones that say pre-Q, that was before, and the ones that post-Q is after. So you'll notice within the triplicate before, I've got like a 75, a 74, and a 97, whereas after, it was like all in the 70s. D7, 83% heterozygosity, a 50 and a 51. After, they were all in the 80s. And you could see that even though the heterozygosity did change within the triplicate, it did get a lot better. And that continues on. So the heterozygosity somehow balanced itself out when I didn't add all of the amplified DNA to the cleanup process. I only added some. Now, major and minor mixtures. 2 mixture ratios were run through the cleanup process on the QIAcube. The ratios of minor to major were 1 to 15 and 1 to 20. In both cases, all of the amplified product was cleaned up. All of the resulting cleanup product was added to the genetic analyzer. The minor peak heights increased, so peaks that were previously not called now were called. The major peak heights also increased, so much so that the major peaks were now all off scale. And that was a problem I encountered with mixtures that high. Because you had your major was there before, and it was already at a high enough level. When you ran that through the MinElute process, the major obviously went way up and went off scale. This introduced things like pull-up to the sample. And in some cases, the pull-up it introduced was as high or higher than the minor. So even though the minor did get pull-up to a callable level that it wasn't before, it was now mixed in with pull-up. As you can see from this diagram here, you've got the major peaks listed there, and you've got the minor. My minor in this case was the 28, and there was a minor in the 30. But you can see peak heights like 32. Look how high that 32 is. That's at like nearly 2,000 RFUs. And that is resulting from pull-up in another marker. I have seen where, like I said, if you have a total low-level mixture, you can bring the entire low-level mixture up using MinElute. But if you have a situation where you have a very high major and a very low minor, unfortunately, when it'll increase the minor, but it's also going to increase the major. Okay, as shown in the previous slide, the minor is well above calling levels. However, many other call peaks are introduced into the mixture due to pull-up from off-scale peaks from the major. These extra peak heights can easily cause the analyst to make an incorrect deduction of the profile of the minor. If the entire mixture is at a low level, then MinElute would be effective. However, when the major is at a normal RFU levels, there is a potential to cause off-scale data with MinElute. This causes subsequent problems that could affect interpretation. So basically, in summary, the MinElute system, whether performed manually or within the QIAcube, increases the peak heights of the data. MinElute cannot correct problems associated with amplification of low-level samples. However, peaks present prior to cleanup, whether previously visible in the baseline, will not only become visible, they will also be called. Each laboratory will need to determine the lowest concentration they want to process when using the MinElute. This value will be determined during their internal validation process. MinElute is a great tool for data that can be seen but not reported out due to the lab's thresholds. It will also reveal any problems with contamination that may have been hidden before. Even though there is a large increase in peak heights with more than one manual wash, the QuickCube gives more consistent results and allows the analyst to do other tasks during the cleanup process. Basically, I mean, my biggest thing with the MinElute was, I mean, I'm sure in casework you've all had that sample where you can see a full profile, but it's below your calling level. And you're like, I can see it and there's nothing I can do about it. I can't report it out. You know, yes, I mean, maybe you could do an exclusion or something like that, but you know, if it's the guy you're trying to get, then you're like, it just kind of hurts to say I have to ignore this data because I can't do anything. That's where, to me, something like the MinElute comes up. You take that, you run it through, you already have your profile there at a low level. You run it through the MinElute so you can confirm, you know, for like a defense attorney, I'm not saying in your mind you'd have to confirm that it's still the same profile that's being pulled up. But if somebody wanted to say, oh, you just produced a new profile, you can show at low levels it was there. But you know, you run it through the MinElute process, and now you've got a profile. A full profile is at callable levels and is easy for you to interpret. And that's basically one of the main uses I see for the MinElute is those samples that are just there, but you just can't do anything about them due to your interpretation guidelines. Any questions?
I know they're hard to reproduce and to capture, but when you did the wash study, you mostly did it on peak height.
Yeah.
But did you look at inserting some sort of contaminant, something you could measure, and see if it affected that? Because we talked a little bit about the washes, and then sometimes they go away, sometimes they don't, but they're at least improved. So did you look at some sort of contaminant? I mean, it's hard to introduce.
Yeah, I didn't do anything with any contaminants for the wash study. No, I didn't. I was just basically with the washes, I was just trying to look at, see if it affected peak heights, because I had seen other papers where they weren't reporting out. When I first did the 4 washes, I was getting these like huge fold increases. And I was seeing other people's work where they weren't getting increases as large, and I was wondering what was the difference. And that's why I wanted to do the wash study, because I know that some people only did 1 or 2 washes, and I was doing 4 washes initially. So that's why I did the wash studies, mostly to just see if the washes do affect peak heights. And what would probably be the most efficient method if you're employing it into your laboratory system and you're going to do it manually. You know, you may say, like, you may put in your protocol, you know, we always do 2 washes, or we only do 1 wash. Because after a certain point, you'll just be using reagents. You won't get the kind of peak heights. Like at 4 washes, I don't think is actually practical. Yes?
Did you do like a time study, like how good the product is after you do this?
I didn't do an official time study. I have left it overnight and refrigerated, like I would leave regular DNA, amplified DNA. So I have stored it overnight. Actually, I've stored it for a couple days, sometimes a week, because I just wasn't able to run it. It's not like an official time study, but I've treated like regular amplified DNA.
So you haven't done it like up to 2 weeks or 3 weeks or 4
No,
weeks?
I haven't done that, no. Which that is something that I could do in the future. Perhaps do like frozen, because I know a lot of people store the amplified DNA frozen.
Maybe an extension of that would be using like the QIAsafe as well, because it could be used for amplified product as well.
Okay, yeah.
You can do room temperature, you know, alternative storage methods too.
Yeah, because there is a QIAsafe which is used, you can store your product at room temperature, which we haven't gone into that, doing one of those studies yet, but that is something that I know a lot of laboratories, and especially small agencies, where you don't maybe have if you store your product for a long period of time, if you have to keep it forever, or sometimes you may have like 100 years or something for murder cases, you know, they have little rules on some types of evidence. If you consider it evidence, it'd be easier to store those things at room temperature as opposed to being in a freezer for that long a time.